Okay, what I want to do in the next few minutes is do a brief summary of Chapter 9. And I'm clearly not going to be covering all the sections, only Section 1 and 2, and only certain parts of them. This this chapter explains how to do this regression work in a couple of different ways, but we're going to highlight really just one. So, correlation and regression looks at bivariate data analysis. And by bivariate, we mean that these are trying to examine the relationship between X and Y variables, so two different variables, one of which will be considered the independent variable and one of them the dependent variable. So a good example would be, for example, if you take your child to a pediatrician, one of the things they always do is get their age, their weight, and their height. And if you looked at age, which should be considered the independent variable, right? We don't have anything to do with aging. It's just something that happens. So anything that involves time always becomes the independent variable. And then say height. Then what you expect to see is as someone gets older, they also get taller, at least through their growth years. And so when you do a bivariate data analysis, you're looking for a relationship between these two variables. Height is the response variable or the dependent variable y. And in all cases, we could consider several different types of mathematical relationship. But in this introductory stats course, we're restricting ourselves to looking at one and only one model, and that's a linear model, okay? And by that, we mean a straight line model. Now, because this is real data, we don't actually expect to get a perfectly straight line, right? Like I've shown here. Instead, we expect, to have data points that are, kind of scattered around a obviously upward moving tendency here. And it would be accurate to say that the expected model shows that as you get older, you also get taller. Okay, and again, we have to restrict that to certain ages because we don't grow our entire lives. Basically, the pediatrician looks at the years from 0 to 18 at the maximum. Okay, so we're going to be only considering this linear model. And I want to show you a picture. Here, I'm going to change the share and show you a picture of several realistic data pieces. So now you're looking at a picture that shows in this upper left-hand corner a relationship very much like what I started out with age and height. And here it's number of movie tickets and total cost. It's reasonable to expect that as the number of tickets you buy goes up, so does your total cost in dollars. And in fact, that's an exactly straight line relationship. With this one, this is data that is height and shoe size. And again, we see a relationship, but it's not strictly straight line, but it suggests that a straight line model going upward from the lower left to the upper right is something that is reasonable for that those two variables. Now, let me point out, and you may or probably already know this, but just like the English language, graphs should be read from left to right. Okay, so in the next one, you see there's a scattering of points, and really that's not a very good linear relationship. It's not as bad as this one down below it, where I really don't see any linearity at all. And then notice to these two that are on the lower row, they have linearity, but the line is going down from left to right and not up like the first ones were. What we do when we look at a linear model, and I'm going to go back and share my presenter window again, is we look for an algebraic relationship that we can express in this way. And if you've had algebra, and I'm sure most of you have, then you would say this is the old-fashioned linear model, y equals mx, m times x plus b. And in that, your two variables are x and y. The m represents slope, which is the rate of change of the x variable, and the b represents the y-intercept, or where the line crosses the y-axis. So let me actually go back as quickly as I can to that picture again. And you should be able to see that if I drew a straight line through this particular upper left-hand corner graph, it has a slope that is positive because as x is increasing, y is also increasing. Okay, so the rate of change of x is positive. When linear models go up from the lower left to the upper right, you call that a positive slope. And then this one would also have a positive slope. The y-intercept clearly in the first one is at 0 on the y-axis. On the second one, it's hard to tell. From this particular picture, I don't have the regression line, so I can't define what y is. But I can say that if you look at these two in the lower corner, now as x increases, y decreases, and this is a negatively sloped line. You're going downhill. And so the rate of change of x is negative. And I can tell from this that the y-intercept for this one is at 100. So you also have a negative slope in this second one. Okay, so with that in mind, that's the kind of model that we want to use as a linear model. And we're going to look at two different ways of getting this linear regression model. One of them I'll show you on the calculator, but I expect you to use StatCrunch much more frequently. So in general, we're going to use these steps. We're going to look at the scatter plot, and we're going to test the validity of the linear model. To do that, we're going to find the value of a thing called the linear correlation coefficient. It has a grisly formula, which is on page, let's see, 473 in the textbook. Now, you will never have to calculate that. Both the calculator program and StatCrunch will give you the value of the linear correlation coefficient. But let me say in advance that the linear correlation coefficient, okay, so linear correlation coefficient always lies between -1 and +1, and it can include them. If it is exactly equal to -1, it is a perfectly straight line. And really the word I should be using is collinear. It's all of the points are collinear. And it has a negative slope. Okay, now notice what I'm implying here is that the linear correlation coefficient can tell us how perfect the linear model is, and it can tell us the sign of the slope. But the linear correlation coefficient itself is not equal to the value of the slope. It tells us whether it's negative going down from left to right or positive going up from left to right. On the other side, of course, this is a perfect positive line, and I should say positively sloped line. So the R can be between these two values, but when it gets in the range around 0, it shows no linearity. So let me go back again. Sorry about all the going back and forth, but it's important. To these pictures. This one here is perfectly collinear, and it goes up from left to right. That has an R value, a calculated correlation coefficient value of 1. This, it's not perfectly collinear, that's clear, but it seems to have a pretty strong correlation going from lower left to upper right. And if you calculated the linear correlation coefficient for those points, you would actually find that it equals 0.81. So it's close to +1. We call that a strong positive correlation. In this one, there seems to be a hint of an upward movement, but it's weak. And in fact, if you calculated the correlation coefficient for these points, you would find that it would be equal to 0.45. You see how this is getting closer to that center point of 0? If you look at this scatter plot in this corner, these points actually yield a linear correlation coefficient of 0.04, so very close to 0. And there really is no linear correlation that is noticeable here. On the other hand, if you look at this one here in the lower left corner, those are perfectly collinear, but they go down from left to right. That has a calculated correlation coefficient of -1. These are not perfectly collinear, but they have a strong negative correlation, and it is at correlation coefficient R equals -0.92. So here's a couple of very important points. The sign of the correlation coefficient is the same as the sign of the slope. So both of these two have positive slopes. And both of these two have negative slopes. The closer the value of the correlation coefficient is to 1 in the positive direction or -1 in the negative direction, the more perfectly collinear the points actually are. And the value of the correlation coefficient will become important, but mostly for comparison to a standard to determine whether or not a linear model is a good model for that data. Okay? But any group of points, you can do the math to get a linear correlation coefficient. So it's an important indicator of linearity, but by itself, it doesn't mean too much. So what we want to do is find that value, and then we want to compare it to a standard. In this case, we're going to compare it to what is called the Pearson value for a specific number of points. Now, I've noted that this is on table 11 on page 477, but let me show you the Pearson chart. So when you are making the comparison, you take the absolute value of the correlation coefficient, which means the number without any regard for sign, okay, the absolute value, and then you count how many data points you have and what significance level you're working on. So typically you use this column that is alpha equals 0.05, and you compare the Pearson value for the specific number of points in your graph with the calculated linear coefficient, its absolute value. And I'm going to show you how to do that. But when you do that, let's see. Formally, it looks like this. When the absolute value of the correlation coefficient is greater than the Pearson value, you find that there is a valid linear relationship between those points. Now, every single set of compared points will give you a regression equation. I mean, that's just a little trick of arithmetic, okay? That doesn't make the regression equation useful. You can only use the regression equation if the linear relationship is valid. Okay, so let me go. I would like to do a problem out of the textbook to try to make this more clear. And so I'm actually going to look at number 23 on page 482. So what I need to do is share my screen. And then I already have up here, if I can get this to go. Okay. Is StatCrunch for the data sets in your textbook. So I'm going to click on that, and I'm going to go to chapter 9. And I'm going to go to section 9.1, exercise 23. Okay, and what that does is it automatically loads the data into a StatCrunch window. Okay, so let's say that your task was to determine whether there was a valid linear relationship here. So the first thing I'm going to do is look at a scatter plot. I'm going to do that by just going to graph and going down here to scatter plot. And I'm going to say the X's are in the column labeled age, the Y's are in the column labeled number of words, and then I'm going to hit compute. Now here's what the scatter plot looks like. Okay? And to me, it looks like, yeah, a positive linear correlation is possible here. Okay? And so I'm going to go ahead and do a formal analysis. And I'm going to show you how to do this 2 ways, all right? So the first way, and the way I expect most everyone is going to use, is to do it using StatCrunch. So to do that, I'm going to go to Stat. And there is a handout in your course content area, Unit 5, about this. Okay, so I'm going to go to Stat. I'm going to go down here to what says Regression, and then over to the one that says Simple Linear. Click on it, and again, the X variable is age, and the Y variable is number of words. I'm going to hit Compute. And this has 2 results. Okay, one of them is this, and I'm going to explain that to you in just a second. But I'm going to look at the other one first. That is again the scatter plot, but notice a red line has been added. The red line is the regression line, the proposed linear model. Okay, and honestly, it's pretty convincing. I think that's probably valid, but I don't get to make that as a choice. So I'm going to go back to my first set of results, and I'm going to look up here, okay? The first thing I want to point out to you is that right here, that is the calculated correlation coefficient, okay, R. And I usually put CALC for calculated to indicate to me that that was something that was calculated based upon the data, okay? And then I want to see that how many points were there. Well, right there it says I had a sample size of 11. Okay, so N equals 11. Now I'm not going to change back to the picture of the Pearson coefficient or the Pearson table. I'm instead just going to look it up. It is, I believe, on page 477. And so you should be able to look at it yourself and see that at 11 pairs of data, the Pearson value, assuming a significance level of 0.05, is 0.602. Okay? Now, the only other thing I want from this table right now, or these results, is this thing right here. Now, they have written out the two variables in words, but I'm not going to do that. I'm going to say number of words, that was the dependent variable, so that's y, equals m is the thing that multiplies by the x value, so it is the 565.26. I've rounded to 2 decimal places. Age was the x value, minus, and or you could say plus a negative, 883.87. Again, I've rounded to 2 decimal places. Okay, so now I'm going to briefly go back and show you what I'm writing down on my presenter window. So this is what I got from my results in StatCrunch, that my calculated R is this. I looked up the Pearson value from table 11 and it's this value. So here's what I have to say. I have to ask myself, is 0.97, and I'm going to round it to 3 places primarily to make it the same length as the Pearson values. Okay, 0.979. Is it greater than or less than or equal to the Pearson value? Well, clearly this calculated R is greater than the Pearson R. And the conclusion I reach is that this is a valid linear model. Now, that's really important because if I were asked to predict the number of words that a child of some other age was, you know, I could do that based upon this model because this model is considered valid. So the ages in our data went from 1 to 6 years old. What I am not allowed to do is extrapolate, which means I can estimate the number of words for any number between 1 and 6, but I cannot estimate the number of words for values that are above 6, because that would extrapolate the model beyond the original data, which is very iffy, you know. Sometimes you can get away with it if the value you're asked to predict is very small, close to the original data, but it's not something you should do. But what if I were asked how many words would I expect a 2.5-year-old to know? Now, what I've done is I've given a specific value to age, X, of 2.5. That is within the range of the values from the original data, so I can make this prediction because my linear model is also considered valid. And what I would do to make that is to simply substitute in to this model the value of 2.5 and solve. And if I do that on my calculator, I get 529.28, so around 530 words. And that is a reasonable kind of prediction. But again, every single set of pairs of data will give you a regression equation. But whether or not you use it in this predictive fashion is dependent upon 2 things. One is you have to prove that the linear model is valid according to this rule about the calculated R being greater than the Pearson R. And the second is that the prediction you are asked to make has an X value that is within the range of the original X values of the original data. Okay, so now I'd like to show you how to do this exact same thing using the calculator. Okay, so if you're using the calculator, and I can see these values over on my screen, but you can't see them right now, but you'll need to trust me. I'm going to go put the data into my calculator. So I'm going to say hit stat, and it's right now on edit, which is what I want it to be on. So I'm going to hit enter, and I'm going to erase the field for X1 and X2, or L1 and L2, and then I'm going to put the age values into list 1. So 1, 2, 3, 4, 5, 6, 3, 5, 2, 4, 6. And then I'm going to put into L2 the number of words. And so it was 3, 220, 540, 1100, 2100, 2600, 730, 2200, 260, 1200, and 2500. Whoops. Okay. You should always check your list. It's really easy to mistype a number. But let's assume I did that correctly. So then I'm going to go to Stat. I'm going to go over to Calculate. Now, it is possible to do this thing from the Test menu or from the Calculate menu. So I'm going to go ahead and go to the Test menu, and I'm going to go down until I find linear regression. There it is, linear regression t-test. So I'm going to hit enter, and it asks me where's the X list. It was in list 1. Where's the Y list? It was in L1. A frequency just means how often do I count each point. You count it only once. Then I'm going to go down here and I'm going to choose the not equal to. That's what you should always choose, and it's based upon the idea that you're running this test as a hypothesis test. And to be honest, I don't want to get any further into that than just to tell you to choose row is not equal to 0. And then I'm going to go down and hit calculate. And this is what you get. So I must have mistyped something because I'm not getting the exact same values, which is kind of aggravating. But yeah, I don't know. I must have mistyped something. But this is your A and B values. So B is the slope here. A is the y-intercept, and there is the linear model. When you look at this, you can also see it always gives you R and R squared. R and R squared are your values of, well, R is your linear correlation value. So I don't know what I screwed up here in my typing, but I must have screwed up something. Okay, so in any case, you could do it from either one. And you really should always get the exact same answer, but let's just assume that I mistyped a number. I think you should do it using StatCrunch, primarily because it's just less confusing. So let's look at another problem. And again, I'm going to go back to my screen and go back to, I can make this behave. Come on. Oh, there it goes. Okay. I'm going to do another problem from your textbook. So let's look at a problem from section 9.2. So in section 9.2, it looks at, let's see, let's do number 19, which is about comparing the number of hours spent studying with the resulting test score. So oh, it's not in here, is it? Well, I'll pick another. Honestly, what I'm trying to do is pick one that I know does not have a linear correlation. I'll be honest with you, but yeah. How about 25? So in 25, what you're looking at is the relationship between shoe size and height. So it seems reasonable to think that the taller you are, the larger your shoe size would be. I mean, that seems reasonable to me. But let's look and see if we can prove that. So to do this, I'm going to go to stat, down to regression, over to simple linear, and then the x value is shoe size, and the y value is height. Now, I get asked all the time, how do you tell the difference between x and y? Typically, we follow the following convention. If the data is given in a vertical fashion, as it is here, the first thing mentioned, which is shoe size, is the x variable, and the next one is the y value. If it's given in a horizontal array, then the highest one is the x variable, and the one below is the y variable. If it's written out in an English sentence, the first variable mentioned is typically the x variable, and the second thing mentioned is the y variable. Most of the time, when it's written out, they will actually just say to you, considering the independent variable of shoe size and the dependent variable of height. So normally that's not a big issue. Okay, so I'm going to go ahead and compute it. And then before I analyze the results, I'm going to look at the scatter plot. And you know, it's not perfect, but it actually looks like a reasonable linear correlation here to me. So I'm going to go back to my results, and my results say that I have a calculated R value that is equal to 0.926 when I have 14 pairs of data. The Pearson value for 14 pairs of data at a 0.05 significance level is 0.532. Okay? And then here is the suggested linear relationship. Height, which was y, equals 1.87 times shoe size, which was x, plus 51.36. Okay, so I'm going to go back to my presenter window here. And I've written down the results from that screen. Now, I want to make a comparison between the calculated R and the Pearson R. And when I do that, I'm comparing 0.926 with 0.532. And again, the calculated R is greater than the Pearson R. And what that means is this is a valid linear relationship. And when I find that it is a valid linear relationship, then that means that this linear model is okay to use to make predictions. Okay? Now, let me show you an alternative interpretation using the same kind of system that you used in hypothesis testing. So I'm going to go back to my StatCrunch screen. And notice over here on the far right of these two boxes, it gives you p-values. So it's telling you a p-value for the intercept and the slope, and then down here it's giving you a p-value for the entire regression model. Now notice that p-value is very, very, very small. That p-value of 0.0001 is far smaller than the significance level of 0.05 that we normally use. And again, just like in hypothesis testing, that indicates that we reject the null hypothesis that there is no linear model, and that will indicate that this is a valid linear model. So let me go back to my presenter window and write that down for you. The alternative way of doing it with p-values. You're going to be looking at the p-value for the linear model. So that second table down there. If the p-value is less than the alpha significance level, which is usually 0.05, then it is a valid linear relationship. And so obviously you expect that this method of making the decision will agree with this the other method of making the decision, which of course it does every time. So we would say that whichever one of these you use, and I don't care which one you use, just be prepared to justify it, right? So when the p-value is less than the alpha, it's a linear model. If the Pearson value is greater than the calculated R value, then it is a valid linear model. There is always at least one of these problems on the final exam. And I got to tell you that people always get that right if it is a valid linear model, because the next problem down is going to ask you for a prediction, right? So it might say, like in this case, this was shoe size and height. So it might say what height is a man with size 11 shoes. So first I look and I see that 11 is within the range of the data, and I know it is a valid linear relationship, so I could make a prediction. So all I do is say y equals 1.87 times 11, which is the value of x, which was shoe size, and then I solve that using my calculator. So 1.87 times 11 plus, and I get, so basically 72 inches, which is 6 feet tall. Okay? Now, if I did not find that the linear regression model was correct, I could not make a prediction. And all I would do is offer the mean of the y values. So let me real quickly look at one other problem. And I hope it doesn't have a valid linear relationship. So I am going to go back to my screen. And then I'm going to see about problem 26. Problem 26 is age versus the number of hours that you sleep, okay, for 10 infants, okay? And when I go and do the linear regression here, again, age is the X variable, hours slept is the Y. I'm going to go over and look at it. Oh, okay. Well, this is a linear relationship, but notice that the slope of this line is negative. So when I go back to my computation, here's what I've got. I have a linear model with a negative slope. I'm trying to find a piece of paper here to write on. Okay, the linear model is y is equal to negative 0.78 times x plus 14.42. And have you noticed that I have exchanged the positions of these two terms every time? That's because I am more comfortable giving the slope times the x value plus the y-intercept, the old algebraic model, than the way they have it, which is intercept plus m times x. So forgive me, it's just a little thing. Okay, n equals 10. And R, calculated R, equals negative 0.952. So the Pearson value for 10 pairs of data is 0.632. Okay. So I'm going to go back to my screen here for the presenter window. This is what I've written down about this particular problem. Now, the reason I kept on with this problem, even though it wasn't going to prove the point that I wanted to make, was I want you to see that the calculated R here, according to our system, has to be the absolute value, the numerical value without regard to sign. So that is actually 0.952, and then the Pearson value from the chart, they're all positive. So you compare these two values, and again, the calculated R value, its absolute value is greater than Pearson, and that means this is a valid linear relationship. Okay, so I wasn't successful at finding one out of your textbook that had a failure for this comparison, but let me reiterate that if you find that there is not a valid linear relationship, then you do not use the regression equation for predictions. Instead, the best predicted value is the mean of the y values, which is just y bar, which you can calculate. I think that you will not have any problems in the lab where you might have one problem in the lab where you have to do this. Okay? And all you have to do is take all the y values and find their average, and that's your best prediction. Okay, well, I'm going to stop it at that, and I look forward to seeing your all's labs.